in this section, we're going to talk a little bit about population growth, which often we refer to as exponential. But in reality, most populations don't grow exponentially. They might be able to be modeled exponentially early on, simply because there's an unlimited food supply, relatively speaking, compared to the amount of organisms. But ultimately, the environment is going to put a limit on how much something can grow. For example, if you're looking at a deer population in an area of forest, there's only so much vegetation. So eventually, deer will start to starve because there'll be competition for the food supply. And so the population will stabilize. So what we're going to talk about here is what's called the logistic model. And it's a way of kind of modeling something that's somewhat exponential looking in the beginning, but eventually then levels off toward a stable place called, often referred to as the carrying capacity. The same thing is true, for example, when you look at the spread of disease. If we look at something like the coronavirus, right, ultimately there's a cap on how many people can get the coronavirus. It's the population, right? So it's like 100%. So if you were to graph it in terms of the population, 0 to, let's say, 100%, okay, ultimately, you might have something that starts off initially like this, where it looks like it's growing exponentially, but at some point it's going to curve over because I can never get more than 100% of the people to actually have the coronavirus. Ideally, you don't want it to be 100%, right? It could be a curve that goes down a little bit lower. So for example, suppose maybe only 25% of the population is going to eventually get it. Right? You might have a curve that looks something like this, where the population grows somewhat exponentially, curves over, and looks something like that. So it just depends on, what we know about types of things that we do to try to reduce the percentage of the population that gets the coronavirus. So how do we model this mathematically? Well, just like anything else with differential equations, we actually create an equation that models the reality we want to model. So normally what we would do is if we say things grow at a rate proportional to the amount, okay, we've talked about exponential growth, and early on it's kind of that way, kind of exponential in nature, in which case our population's rate of change normally is proportional to the amount of stuff we've got, the population. Okay, what's a little bit different here is we really don't want this to continue because this would grow unbounded. It'd be an exponential function that grows unbounded. So instead, what we really would like to do is we would like to limit this. So the way we do that, let's say we want to cap at C, referred to as the carrying capacity. Okay. If we want to cap it at the carrying capacity, what we do is we modify by attaching a factor that serves to level it off. Okay, so what we want is we want to grow kind of like this initially, but eventually as the population gets closer and closer to C, we want the slope to go closer and closer to 0. We want it to kind of settle down and level off. So what we can do is we can attach a factor here of C minus P. So what's going to happen is when C and P are relatively far apart, this number is pretty constant, and you can kind of think of it as folding that constant into the constant K, and you still have rate of change is proportional to the amount. But when C and P get close together, this factor approaches 0. Oops, sorry. Okay. Serving to level off the slope to a slope of 0. So we're, in a sense, creating a differential equation that's going to have the behavior we desire. Now, a solution to this, and you can check it using your CAS if you want, but if I look at this function, okay, this will actually be a solution to this differential equation. Let's check it out. Let's define P of t. C divided by 1 plus d. And here d is just a constant that would take into account certain initial conditions. Okay, so d times e raised to the minus k times c times t. All right, so let's try it. Let's take the derivative of this guy with respect to t. Click. Not sure what it's doing. The calculator just hung up on me here. Oh. All right, let's try it again. Derivative with respect to t. P of t. And I get that. So now let's compute this side. So that's k times P of t times the quantity c minus P of t. And we get that. And sure enough, true. Those two sides are equal to each other. So this indeed is a solution to this differential equation. All right. So the nice thing about it is it creates the desired behavior that we want. And so let's take a look at a situation. All right, so let's look at a scenario here, and we'll apply this idea. So suppose a deer population in an area of the forest can only reach, let's say, 1,300 due to food supply. Okay. So suppose we have this, and suppose we also know that what the initial population growth is, and we know about how many deer we start with. So let's say, for example, we start with 132 deer. Growing at a rate of 17 deer per year. Okay, and suppose we want to actually describe this deer population. All right. So we kind of know this scenario here. We know that dp dt, when t is 0, is 17. We know that p of 0, initial population, 132. So we can actually use that information here very easily to solve for k. So that means that we've got 17 is equal to k times the initial population, 132, times carrying capacity, 1,300, minus the initial population at that point in time, which again is 132. So this is going to allow us to solve for k. Well, once we solve for k, here we can actually then solve for D, and we pretty much know everything there is to know. Another thing that we can do is we can actually use this information and model it using a system of equations as well. So I've already defined the function in my machine, in my CAS. So what I can do is I can say, let's take the derivative of this guy, with respect to t. All right, and then I'm going to say such that t equals 0. So I'm going to take the derivative, then I'm going to plug a 0 in for t. So that's giving me this expression. So this is what I want to eventually be 17. And I can also type in p of 0 and get that, and I want that to be 132. So I now have two equations and two unknowns, right? My unknowns, I'm going to use that, these two things, and I'm going to solve for k and d, and then I know everything there is to know about this function. So let me go in and get my algebra command. I'm going to do my solve system of equations here. So I've got two equations. My unknowns are k and d. All right. So I'm going to go up and grab these expressions. That guy, we wanted to be 17. Click down here, get in the box. I'm going to click up here and highlight. Hit enter, copy into the box, say I want that to equal 132, because that's my initial condition here. And I get these values. Oh, I forgot to put in my carrying capacity, sorry. So I'm going to say such that C equals 1300. There we go. All right. And so I end up with D equal to 292 over 33, and K equals 17 over 154,176. So I get these values. So I can, if I want, I can just have my machine define those for me. Define the first one. Define the second one. So now I've got the values for that, and I can, if I want to plot it, take a look at it. My machine now knows what that is. Let me go ahead and define C also. C equals 1300. All right, let's do a quick plot. P of, I got to call it X because I'm on the plotting page. All right, doesn't look like I can see anything because my window is not adjusted. So I'm going to pull that down. Let's plop this guy up to, what did I say, 1300. So let's go to 1500. There it is. If I want, I can grab this axis here, go further out. I'm going to hold my shift key and just adjust that axis. And you can see, as I move out in time, okay, I'm getting this thing leveling off at 1300. How do I know it's 1300? Well, let's just graph 1300. Swing, there it is. So you can see it is approaching that leveling off of 1300. So we basically created a scenario that modeled the desired behavior of the deer population that we wanted to observe, because we had certain information maybe that told us how much food supply was there and therefore how much a deer eats, and this would tell us what the stabling value would be. Okay, so the logistic growth is really handy because the more data we have, the better we can model this curve. And with the coronavirus, it's a very similar sort of thing. You know, we want to be able to see this curve level off sooner than later. So we want the leveling off to be lower when it comes to the virus. And so the data that we gather, if it's accurate data, can help us find a way to do that. So anyway, this is basically the logistic model and how it works.